All right, so continuation from yesterday. I think we stopped at part B on how fast is it moving in inches per minute. Because it's inches per minute, that's how we know we're looking for the linear velocity, okay? So we're looking for the linear velocity. So for linear velocity, the formula is your angular velocity times your radius. Well, we know our angular velocity. This right here is our angular velocity. So we know our angular velocity equals this. So 200 pi divided by 3. Okay. Then our radius. Our radius we discovered was 47/8 inches. And now we're just going to multiply. Okay. So then I like to reduce, then multiply. You're probably like, but why? And I was like, because it just, in my mind, I like to have the smaller numbers. But if I'm plugging it into the calculator, does it really matter? It doesn't, but let me be great, okay? So here we plug into the calculator, we multiply numerator times numerator, denominator times denominator, and we're left with 1175 pi over 3, okay? 1175 pi over 3 is our exact answer. Our approximate answer would be 1175 times pi divided by 3, and that gives us 1,230.5 inches per minute. Okay. That's a fairly large number. So if I'm describing how fast my record player is going, and I say, oh, it's moving 1,230.5 inches per minute, that's like still like, oh, okay, I think that's fast. But we can break it down even more and look at it in terms of feet per second. So this is where we go back to our quote unquote train tracks, right? So for train tracks, again, you want to start with your exact value. So this is our exact, right? That's our exact. So we have 1,175 pi over 3. And this is representing, the numerators are inches, the denominator is our minutes. And now we're going to go from inches to feet. How many inches are in a foot? Inches in a foot. Just 12. 12 inches in 1 foot, right? So now inches are gone. Boop, boop. And then we need to go from minutes to seconds. How many minutes are in a second? Well, 1 minute is 60 seconds. So minutes are gone. So that's how the train tracks work. Like as I'm going along the tracks, I'm trying to cancel one unit to be left with the other unit. So are we left with feet and seconds? Yes, we are. So now you're just multiplying. So 1,175 pi times 1 is just going to be 1,175 pi. 3 times 12 times 60. What is that? That's 2,160. 1175 divided by 2160. There's no point of reducing that. That's our exact. So then what is our approximate speed? Let's see. 1175 times pi divided by 2160. We get roughly 1.71 feet per second. Notice how when I had a fraction as my exact, did I change my numerator to a 1? No, I used the denominator. I used the denominator that was there. So if it's not a 1 in the denominator, use the 3. Okay. That's how the beauty of math. It's going to all end up canceling itself out and being multiplied correctly. So again, with angular and linear velocity, it's about the formulas. Formula, using your formulas. So we talked about the formula, so let's look at them again. So we talked about for angular velocity, you're looking at your theta divided by your t. Okay, so your rotations over your time. When you're looking at linear velocity, there's two ways to look at it. One is your angular times your radius, and the other is your distance, your arc length, divided by your time in terms of a circle, okay? So formula. So on your test on Friday, if you're not gonna be able to memorize these formulas, what should you be putting on your note card? These formulas, right? These 5 formulas so that you have them at your disposal, correct? All right, let's do another one. So here it says, with arms fully extended, a baseball player swings a bat using his shoulder as the center of rotation. The bat moves through 120 degrees in only 0.2 seconds. What is the angular velocity of the batter's swing in radians per second? Okay, so it says in radians per second. Right here, we know that this is degrees per second, right? Degrees over seconds. So based on what we have here, we can figure out his angular velocity equals how many degrees did he go? 120 degrees. And how fast did he go? 0.2 of a second, right? But instead of degrees, they want it in terms of what? Radians, right? So in terms of radians, well, I'm going to set up my train track. How many degrees are in a radian? What's the relationship between a degree and a radian? Well, Ms. Jones, that would be 1 pi radian, right? Is 180 degrees. Could I use 2 pi and 360? Yes, but why would I want to use something bigger when I know that 1 pi radian is 180 degrees? So that gets rid of my degrees. I multiply straight across. I have 120. That's 120 pi over and 0.2 times 80. That's going to give me 16. Okay, so this is my radians per second. Is it reduced? No. Could I reduce it even more? Why, yes, I can.
Who didn't believe in me? Who? Yeah.
Okay, nobody.
Mr. Almond, you should have seen the hassle I went through.
I didn't feel like they really would say anything to you, but for some reason you did.
No, I defeated the system. Yeah.
Okay. All right, 15 pi over 2 radians per second is our exact. So this is our exact. And then we're going to find our approximation. When you're finding the approximation, you're putting the whole thing in the calculator, right? So timesing that. What'd I get? How many? I got 23.7. I feel like I did something wrong. That's bigger than what's in my notes. What did I do? Hold on. Figured it out.
Okay.
What happened? Please excuse. Don't be mad. Don't come for me. Don't attack me. All right, sorry guys. I totally thought my scribble was a scribble and not a 1, and that's why my numbers were weird. So it should have been 0.2 times 180, which is 36. Duh. Okay, and then 120 divided by 36 is 10 pi thirds. So this is 10 pi over 3. And then multiply that and divide. And that's the answer that's in my notes. 10 and 47 radians per second. Y'all didn't want to point out to me that I totally forgot about my 1 on 180? Nobody? Thanks. 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 But my whole 1 was just not acknowledged. To go from degrees to radians, you should know it's pi over 180, guys. Just left me looking like a fool. All right. So this is our angular velocity. Angular velocity equals 10 pi over 3 radians per second. Okay. It says, as he swings the bat, the player hits a baseball. Suppose the ball leaves the bat at a distance of 40 inches from the player's shoulder. How fast in miles per hour would the ball be moving? Okay. So they want to know how fast in miles per hour would the ball be moving? What should we do here? What does the 40 represent? The what? So it's the inches from the shoulder, right? So this is the 40. So this would be what of the circle? If I'm the radius. So the 40 is our radius. So we have 40 inches equals our radius. And we already have our angular velocity. And so if it's miles per hour is what they want, we're gonna have to go from inches and make our way there, right? So first thing, linear velocity equals your angular velocity times your radius. What's our exact value of our angular velocity? This guy, right? 10 pi over 3. And what was our radius? 40. So therefore, our linear velocity, what is 10 times 40? 400 pi over 3. Okay? Our radius is in inches. And the time from our angular is seconds. So this is inches per second. Does it want to know how fast it's moving in inches per second? Miles. We have to convert from the inches per second into miles per hour. Okay, so we're going to set up our tracks. I think I can squeeze it in here. So we have 400 pi inches per 3 seconds. Okay, so inches. How do I go from inches to miles? Feet, and then feet to miles, right? So 12 inches is 1 foot. 1 mile is how many feet? If you did your do now, then you would know. Oh. So how many feet are in a mile?
I had that question. 1,255. 1,255.
No.
2,000 something, right?
5,000. 5,280 feet in a mile.
You were way off.
You were way off.
No, but
Oh, okay. So we went from inches to feet, feet to miles. Okay. Now we got to go from seconds to hours. How many seconds are in 1 hour?
I got this one. No, wait. Oh, minutes,
Yes.
seconds.
How many seconds in an hour?
Okay, it's 36.
3,600. 60 times 60.
I'm-
60 times 60. There's 60 minutes, each 60 seconds.
I'm smart.
And that's 1 hour. I squeezed it in there, guys. I made it. Okay. So now we have everything. So multiply your numerators, multiply your denominators, and divide. Right? That's what we got to do. All right. So we're going to just find the whole 400 times. Oh, that's big. 400 times 3,600. That is 1,440,000. 1,440,000 pi. Then we're going to do the denominator. 3 times 12 times 5,280. And that gives us 190,080. So that's the exact in our miles per hour. How do I find the thingy?
You divide.
You divide it.
You know, I wouldn't actually.
We're gonna reduce this fraction. Fraction reduced would be 250 pi over 33.
That's what I was thinking. Yep.
I knew it. I knew you knew it.
And I feel so smart with this cup.
My great. And that's gonna give me 23 and 0.8 miles per hour. Okay.
Yep.
That was a lot of work.
Ugh.
I should have made this more than one slide. It's all right. We got it. I squeezed it in there. All right. Then during a second time at bat, the player hits another ball, which leaves the bat at a distance of 43 inches from the player's shoulder. How fast in miles per hour would the ball be moving? So this time we would do the same thing, but instead, our radius is now changed. Our radius is now 43 inches. So this is our new R. I'm going to need a whole nother color, or pause. I'm going to switch. All right, we're going to start where we left off yesterday. So yesterday we stopped at example 2, part B. We were finding the linear velocity of the album in inches per minute. So we stopped with our discussion about, do you reduce before or after you multiply? Does it really matter? No, it does not, especially if you're going to be using the calculator to help you reduce. So we got to the point where we found our exact value. So this is our exact value of our linear velocity. And now we're going to find the approximate. So to find the approximate value of our linear velocity, and I'm sorry, I didn't label this. This was our angular velocity. But to find our exact value, we're going to plug that in the calculator as it is. So we're doing 1,175 times pi divided by 3. And we get
1,230.5.
Point.
We're rounding.
Yeah, we'll do 5, 4, 6, 5, whichever, inches per minute. Okay. So now we have a linear speed, right? We have our, but in terms of describing something, telling someone, oh, that record spin at a 1,205.5 inches per minute, that really is like, I think that's fast. Like you're not, what did I say? Spin. I don't know. Spin. You know what I mean? And so we're going to put it now in terms of feet per second. Okay, so we got to convert from inches per minute to feet per second. Okay, hence why your do now had you doing what? If you actually did your do now, like you're supposed to. I'm on it. So your do now has you practicing converting, right? On your do now, you were converting from miles to feet, I think, and out days. Oh no, a year to seconds. So, prepare you for that. All right, but here, linear velocity. So again, when you're converting, you want to use your exact value. So our exact linear value is 1175 pi divided by 3, right? Thirds. Now, when you have a fraction, you can still set up train tracks and get to the same conclusion. I should have made this a little bit bigger and zoomed in. Let's pause for a second and I'm going to do that. All right, so we're going to answer part C, but on the next page. So we need the exact value of our linear velocity. Someone remember, or you guys tell me when I go in case I forget. 1175, right?
Yes.
So we had 1175 pi over 3. And this is in what currently?
Exact.
It's exact, but what are our units? Inches per second. So we're in inches per second. Okay. When it's a fraction, whether you put the whole fraction in the numerator or you have the numerator stays numerator and the fraction becomes your seconds, it still is going to come out to be the same thing. Okay. So just let numerator be your distance, denominator be your time. And now we're going to convert. So I need to get rid of inches and turn inches into feet. How do I do that?
Put the inches in the denominator.
Inches in the denominator.
And 12 inches equals 1 foot.
There we go. So now inches are gone. I need to go from seconds, not seconds. Was it seconds?
I think it's minutes.
Minutes. Let me go back and look. What was our original time? Minutes. Fiddle farts. My bad, bro. My bad. Minutes. There we go. You never saw anything. I need to go from minutes to seconds. So how do I do that? Minutes in the numerator.
1 minute equals 60 seconds.
1 minute equals 60 seconds. Am I down to the units that I want?
Yeah.
Yes. Ouch. I am. So I'm going to multiply straight across numerator times numerator and denominators times denominators. So we have 1,175 pi all over. And what's 3 times 12 times 60?
2,160. No, I used to calculate. Thank you, Des.
All right. So that's our exact value, right? So our exact value is this. Could we reduce it? Yes. But in reality, we want the approximate. So there's no point of reducing this at the moment unless we needed it again. So this is our feet per second. And now we're going to reduce this by find the approximate by plugging it all into the calculator. So 1,175 times pi divided by 2160 gives us
1.708.
so 1.71 feet per second. So now when I tell you, oh, this record is moving at 1.71 feet per second, is that fast? Yeah, that's pretty fast. I think it's fast. Like in my mind, a foot, 12 inches every second. Rotating. It's the album spinning.
I feel like RPM.
It would, I guess. But we're gonna keep going.
Only if you're rolling it across the floor.
One,
Yes.
2 feet a second.
I think.
It's like.
It's moving, but not as fast. Okay, hey, we're there, we're good.
I figured it out.
Oh.
You really need 0.0372 miles cubed of cloud.
Okay, cool, exciting. Here we go. Example 3. Oh, example 3. With his arm fully extended, a baseball player swings a bat. Using his shoulder as the center of rotation, the bat moves through 120 degrees in only 0.2 seconds. What is the angular velocity of the batter's swing in radians per second? Okay, so angular velocity equals our theta in radians times our radius, right? So the first thing that you do is figure out what is our theta. So our theta in radians would be, how do I convert 120 degrees into radians?
Yeah.
Times pi over 180. Okay, and this simplifies down to 2/3 pi, right? Because 12 and 18 both divide by 6. So now we have our theta. Our radius is the length, not our radius. Where are we at? Oh, I don't need radius. We already had that. We just need 2 pi over 3, and then we have our time. My bad, guys. My bad. Where am I at? Radius per second. We did it. I'm there. I'm sorry. I'm in my head on my own. So we have our radians and we have our seconds. And how many seconds do we have? 0.2 seconds. Okay. So radians, seconds, I just got to do what? Simplify that, right? So 2 pi thirds divided by 0.2 is going to give me my radians per second. And what is that?
I'm checking. 10.47. Does that sound right?
Sounds right. Sounds like what I got earlier.
Yeah.
Yeah. Good job.
Mm-hmm.
So 10 and 47 radians per second. I don't know what I was about to make y'all do it earlier. Okay. So again, we found our theta. And our angular velocity was already given to us for the most part. Okay. So in this case, we didn't need the radius because we had our time. And so because we had our time, it satisfied our radius. Now, let's go here. Okay. So using what we have, it says as he swings the bat, the player hits. That's what I did. Ignore that. Ignore all of that. Just need that. Angular velocity equals. I'm sorry. I'm in my own head about things right now. Anyways, as he swings the bat, the player hits a baseball. Suppose the ball leaves the bat at a distance of 40 inches from the player's shoulder. How fast in miles per hour should the ball be moving? Okay. So in this case, we're looking for our linear speed because it says miles per hour, right? That's our distance. So we know that VL equals, and in terms of our problem, it's our angular velocity times our radius, right? And we've already determined the angular velocity, and our angular velocity equaled 10.47. We probably should have found the exact. Are y'all okay if we move through with the approximate?
Sure.
Are y'all cool with that? Cool. Okay, so we know that our angular velocity is 10 and 47 hundredths radians per second, and our radius is going to be the arm, the distance. So then we're going to plug that in. So we have 10 and 47 hundredths times 40, and that equals. Someone with a calculator.
Oh, sorry. Times 40.
Or something.
418.8.
There we go. Inches per second. Okay. Does it want it in inches per second?
Miles per hour.
It wanted it in miles per hour. So we have to convert, right? So I'm going to have to take the 418.88 inches per second and convert it into miles per hour. Let's begin. So we have 418.88 inches over 1 second. How do inches become miles? Where should I go to first?
Inches in the denominator.
Inches are in the denominator. Probably should go to feet first, right?
Yeah.
So 12 inches is 1 foot. Inches are gone. How do feet become miles? Good job. You must have done your do now. And that is 1 mile. Feet are gone, down to miles. Now I need to go from seconds to hours. How many seconds are in an hour? There's 60 minutes, 60 seconds, guys. There we go. There's 3,600 seconds in 1 hour. All right. Am I down to the units that I want?
Yeah.
Yes, I am. So I'm going to multiply everything in the numerator, everything in the denominator, and then divide. I don't want to do it separately, so I'm going to do it all together. So we have 418.88 times 3,600 divided by 12 times 5,280. Oh, like what's wrong?
Ooh, that's a big number.
Not if you do it all together. 23 miles per hour. Okay, so literally in the calculator, I just typed in the numerator values and multiplied, typed in the denominator values and multiplied, and divided the two answers, right? Or you can type it all in at once, however you want to do it, but. Okay. Huh? All right, so next. We have, during the second time at bat, the player hits another ball, which leaves the bat at a distance of 43 inches from the player's shoulder. How fast in miles per hour would this ball be moving? Okay, so this ball, our R has changed, right? So I would like for you to take a moment to find the speed of this ball. Huh? Look at how we did B, and this time you're doing it with C. Your radius has changed.
It's gonna get faster eventually with this.
Here we go. So we are doing exactly what you should have did exactly what we did on example 3B, right? The only difference is that instead of 40, it changed into a 43. So your linear velocity here equals 43 now, still the same speed. And you plugged it in and you should have gotten
450.2. I got one.
my note says 29. I think because I did with the whole thing earlier.
This one I got.
Desmo says 2-1.
Oh, yeah, my calculator says 2-1-2.
I said I think because I took my notes doing it with the exact values.
Oh, I think.
Yeah. I'm sorry. I did, yeah. All right, and then when you convert it, what did it come out to be? How fast was the ball moving in miles per hour?
I didn't get that far. We'll start somewhere.
So when we're doing that, remember how this was 418? This is now replaced with the 450, right?
Yep.
And then everything else is going to be the same. So to get it, you should have had 450.29 times
3,600.
3,600,
And that equals.
and then divided by, what was the bottom? 12 and 5. 12 times 5,280. And we're looking at approximately,
I can 25.58.
5.8, can I put 6?
Yeah.
Miles per hour.
No, you're a 5-8 like me.
Oh, my bad, my bad. Okay, so now it's all together on your paper.
It's number 3.
Yeah.
That's what we've been working on this whole time, right?
We did example 2 and then example 3.
You wrote it on the one. You using that
Uh,
paper?
Why are you using that paper?
Huh? You write on a separate paper. Are you serious?
I said that yesterday. I said I messed up the print, but I wanted y'all to still have the words.
I was running on the paper.
Are you making it fit? Oh, okay.
Yeah, it was good. If it didn't fit, I just wrote it bigger. So I can read it.
Okay. All right. So that concludes the first part of this.
Oh.
Yeah.